Ventnor, Isle of Wight, August 12, 1940, 11:51 hours. And Women's Auxiliary Air Force operator Elizabeth Henderson sits before a cathode ray tube in a wooden hut that smells of electrical equipment and nervous sweat, watching a blip on her screen that represents death approaching from across the English Channel. The green phosphor glow shows what appears to be 60 or more aircraft forming up over France, and she knows with absolute certainty that within minutes, Juncker's 88 bombers will be screaming toward her position, trying to destroy the very equipment she's using to track them. What the Luftwaffe pilots climbing into their cockpits at bases near Cherbourg cannot possibly understand is that the tall steel towers they've been ordered to bomb, those strange lattice structures rising 360 feet into the British sky, represent a technological revolution that has already made their carefully planned invasion of Britain almost impossible. And within hours, their bombs will temporarily silence one of these towers, but the British will perform an act of deception so clever that the German High Command will conclude that radar stations are indestructible, abandoning attacks on the very weapon that is defeating them. The story of how Britain developed the world's first integrated air defence radar network begins not with military planning or vast industrial programs, but with a Scottish physicist's response to a question about death rays. In January 1935, rumours circulated through British military circles that Nazi Germany had developed some kind of radio weapon capable of destroying aircraft in flight, a death ray from the science fiction stories that filled popular magazines. Harry Wimperis, Director of Scientific Research at the Air Ministry, asked Robert Watson Watt, a radio researcher at the National Physical Laboratory, whether Britain could develop a similar weapon to defend against German bombers. Watson Watt's assistant, Arnold Wilkins, performed calculations showing that a radio death ray was impossible with existing technology. The power requirements would be astronomical, but Wilkins suggested something that seemed almost mundane by comparison, yet would prove far more valuable. If radio waves couldn't destroy aircraft, perhaps they could detect them, bouncing signals off metal hulls and measuring the return echo to determine range and bearing. On February 26, 1935, in a field near Daventry, Northamptonshire, Watson, Watt and Wilkins demonstrated their concept to a single observer from the Air Ministry's Committee for the Scientific Survey of Air Defence. They positioned receiving antennas about 6 miles from one of the BBC's shortwave broadcast stations and arranged for an RAF Handley Page Hayford bomber to fly a circuit in the area. The two antennas were carefully phased so that signals travelling directly from the BBC transmitter cancelled themselves out, but signals arriving from different angles, reflected off the bomber's metal structure, would deflect the trace on a cathode ray tube indicator. As the bomber flew its pattern, Watson, Watt and Wilkins watched their oscilloscope screen, and there, appearing as a distinct deflection in the trace, was the echo from the aircraft. The signal was incredibly weak, roughly 1/10 quintillionth of the transmitted power, but it was detectable, measurable, and most importantly, it worked. The British government, recognising the potential of what they'd witnessed, immediately provided funding for further development, understanding that this radio detection finding system, later abbreviated to the term radar, might give them the early warning capability that could mean the difference between survival and defeat in a coming war with Germany. Watson Watt and his team, now including young physicist Edward Bowen, moved their research to Orford Ness, an isolated peninsula on the Suffolk coast, where they could test their equipment without interference and in secrecy. By June 1935, just 4 months after the Daventry demonstration, they were detecting aircraft at ranges of 16 miles, far enough to make the Air Ministry cancel all competing sound-based aircraft detection systems. By the end of 1935, the range had increased to 60 miles, and plans were underway to construct a chain of radar stations covering the approaches to London. The technology they developed used powerful transmitters sending pulses of radio energy from antennas hung between steel towers over 350 feet tall, with separate receiving towers arranged in a configuration that allowed operators to determine not just the range to detected aircraft, but also their approximate bearing. The system was primitive by later standards, using long wavelength signals that couldn't produce narrow beams like modern radar, instead illuminating huge areas of sky and using clever goniometer techniques to measure the direction of returning echoes. But it worked, and more importantly, it could be built quickly using existing components rather than waiting for perfect technology that might arrive too late. In 1936, the research team moved to Bawdsey Manor on the Suffolk coast, which became the headquarters for all British radar development and the site of the first operational chain-home station. By 1937, the first 5 stations were complete, covering the approaches to London, and by 1938, they were conducting full-time operations. But the early trials revealed a problem that had nothing to do with the radar technology itself. During tests where ground controllers attempted to direct fighter aircraft to intercept practice raids, the system failed spectacularly. Fighters arrived too late or went to the wrong locations, and bombers reached their targets unmolested. Air Chief Marshal Hugh Dowding, commanding RAF Fighter Command, watched one such exercise with growing frustration, listening to confused radio chatter while the practice bombers he could actually hear overhead remained unintercepted. Dowding quickly identified the problem, not the radar detection, but the information management system. Radar operators were sending reports directly to fighter squadrons. Multiple stations were reporting the same aircraft, causing confusion, and there was no coordination of the information to create a coherent picture of what was actually happening in the sky. Dowding, along with physicist Henry Tizard and others, designed what became known as the Dowding system, an integrated command and control network that transformed raw radar data into actionable intelligence. The system worked through multiple layers. Radar stations along the coast detected incoming aircraft and telephoned their reports to a filter room at Fighter Command headquarters at Bentley Priory, where specially trained personnel compared reports from multiple stations, eliminated duplicates, and determined the actual number, bearing, altitude, and identity of aircraft. This filtered information was then plotted on large maps in group and sector operations rooms, where controllers could see the developing situation and direct fighter squadrons to intercept specific raids. The system also integrated reports from the Observer Corps, thousands of volunteers stationed at posts throughout Britain, who visually tracked aircraft once they crossed the coast and the radar could no longer see them. The entire network was connected by thousands of miles of dedicated telephone lines, creating a communications web that could relay information from detection to fighter pilots in minutes, rather than the hours that conventional military communication systems required. The Dowding system was manpower intensive, requiring thousands of operators, plotters, and controllers working in shifts around the clock, but it multiplied the effectiveness of Britain's fighter force to an extraordinary degree. By September 1939, when Germany invaded Poland and Britain declared war, 21 chain-home stations were operational, covering most of Britain's eastern and southern coasts from Southampton to the Scottish border. The network could detect aircraft forming up over France at ranges of up to 80 miles, giving Fighter Command precious time to scramble Spitfires and Hurricanes and position them to intercept raids before they reached their targets. This early warning capability proved its worth immediately during the early months of the war, when German bombers attacking coastal convoys found RAF fighters waiting for them, despite the Germans approaching over open water where visual spotting was impossible. But the chain-home system had a significant weakness that German intelligence would eventually discover. The radar was optimized for detecting aircraft flying at medium to high altitudes, above about 5,000 feet, and had difficulty seeing low-flying aircraft because the radar beams swept out over the ocean at an angle that left a blind zone close to the surface. British engineers recognized this vulnerability and developed Chain Home Low, a supplementary network of 30 smaller stations using different technology that could detect aircraft flying as low as 500 feet, though at shorter ranges than the main Chain Home system. By the summer of 1940, the two systems together provided coverage from ground level to 40,000 feet, creating an invisible fence around Britain that made surprise air attack almost impossible. The Germans knew about the British radar towers. The massive steel structures were visible from the French coast, impossible to hide, and German intelligence aircraft had photographed them extensively. In May through August 1939, the Graf Zeppelin II, Germany's newest airship, made multiple flights along Britain's North Sea coast, specifically to investigate these mysterious towers, carrying equipment to detect and analyse radio signals. German technicians aboard the airship did detect the 12-metre wavelength pulses from chain-home stations, and some suspected they were dealing with radar, but the chief investigator couldn't prove his hypothesis, and German High Command received conflicting reports about what the towers actually did. This confusion stemmed partly from German assumptions about radar technology. The Germans were developing their own radar called Freya, which used much shorter wavelengths and produced narrow beams, and they found it hard to believe that the British system using such long wavelengths could be effective. During the Battle of France in 1940, German forces advancing toward the Channel coast detected the 12-meter signals and finally confirmed they were dealing with radar. But even then, German commanders didn't fully grasp the strategic importance of the system they faced. The Luftwaffe's confidence in the summer of 1940 came from their stunning victories across Europe, the destruction of the Polish Air Force in days, the defeat of France in weeks, and their overwhelming numerical superiority over the RAF. The Germans could field over 2,400 fighters and bombers against Britain's roughly 900 fighters, and their crews were experienced, well-trained, and led by commanders who believed they understood aerial warfare. But their doctrine was built around the idea that bombers approaching at altitude could overwhelm defences through sheer numbers, that fighter interceptions would be random and ineffective because defenders couldn't know where or when attacks would come, and that sustained bombing would destroy the RAF on the ground before it could effectively respond. What Hermann Goering and his staff failed to comprehend was that radar had fundamentally changed the mathematics of air defence, allowing the British to concentrate their limited fighters at precisely the right place and time, turning what should have been hopeless odds into a contest the RAF could actually win. The chain-home system effectively multiplied Britain's fighter strength by a factor of 3 or more, because aircraft didn't need to fly constant patrols burning fuel and exhausting pilots. They could wait on the ground until radar detected incoming raids, then scramble and climb to intercept, with ground controllers guiding them directly to the enemy formations. On August 12, 1940, the Luftwaffe finally launched a coordinated attack against the radar system they'd been ignoring. The operation, planned as part of Adlertag or Eagle Day, the beginning of the air offensive meant to destroy the RAF and clear the way for invasion, included strikes on 4 chain-home stations: Dover, Pevensey, Rye and Ventnor. At 9 o'clock in the morning, fighter bombers from Erprobungsgruppe 210, an elite unit flying Messerschmitt 109s and 109s configured to carry bombs, screened in at low altitude toward Dover, Rye and Pevensey, catching the stations with minimal warning because they approached below the effective detection height of the radar they were attacking. At Dover, bombs damaged some of the radio towers and destroyed several huts, but the station remained partially operational. At Rye, the power supply was knocked out, but technicians had the station running on emergency generators within hours. At Pevensey, a bomb cut the main power cable, and the station went completely silent, a 100-mile gap suddenly opening in Britain's radar fence. At Dunkirk Station near Canterbury, bombs destroyed 2 buildings, but missed the critical equipment, and the station continued operating. Then, at 11:51, a much larger force appeared on the surviving radar screens. 63 Junkers 88 bombers, escorted by over 100 Messerschmitt fighters, approaching from the direction of Cherbourg. The formation split as it crossed the coast, most of the bombers heading for Portsmouth Harbour, but 15 Ju-88s broke away and turned toward Ventnor on the Isle of Wight, the chain-home station that covered the approaches to Southampton and the Central Channel. The operators at Ventnor had been tracking this raid since it formed up over France, watching the blips on their screens grow stronger as the Germans approached, knowing with absolute certainty that they were the target, that within minutes bombs would be falling on their position. The WAF operators, young women, many of them barely out of their teens, stayed at their posts, transmitting bearing and range data, even as the first bombs began to fall, professional to the last second, before they were ordered to the shelters. The Ju-88s, diving from 12,000 feet with the precision that German bomber crews were famous for, placed their bombs with devastating accuracy. High explosive and incendiary bombs tore through the wooden receiver huts, starting fires that quickly engulfed the delicate equipment inside. The transmitter block took direct hits, and though the tall steel towers survived, their open lattice construction making them surprisingly resistant to blast damage, the station's underground cable connections were severed, power supplies destroyed, and backup generators damaged beyond immediate repair. As the smoke cleared, and the sound of aircraft engines faded toward France, the assessment was grim. Ventnor was completely off the air, the most thorough destruction of any chain-home station so far in the war. RAF fighters had been scrambled, nearly 60 Hurricanes and Spitfires from 4 squadrons, but they'd arrived too late to prevent the bombing. A bitter irony, given that the radar had provided plenty of warning, but couldn't protect itself. The station commander surveyed the damage and reported to Fighter Command headquarters that Ventnor would be out of action for at least 2 weeks, possibly longer. A 100-mile gap now existed in Britain's radar coverage, from the eastern end of the Isle of Wight to beyond Portsmouth, through which German aircraft could approach undetected. German reconnaissance flights that evening and the next day monitored British radio signals, listening for the distinctive 12-metre pulses from the chain home stations, and their report should have been encouraging. The Ventnor signal was absent, the station was confirmed destroyed. But before that reconnaissance could be completed, British engineers executed a deception that would have enormous consequences. While repair crews worked desperately to restore Ventnor's equipment, other engineers at the nearby Bembridge station, which had not been attacked, reconfigured their transmitters to broadcast signals identical to those Ventnor had been sending. They carefully matched the frequency, pulse rate, and power output, creating the illusion that Ventnor was still operational, still sweeping its radio beams across the channel looking for German aircraft. The deception was crude, the fake signals couldn't actually detect anything, and the gap in radar coverage remained real. But to German listening posts in France, it appeared that their carefully planned attack had failed. When Luftwaffe intelligence officers reported that, despite the visible damage and obvious success of the bombing, the Ventnor station was still transmitting its characteristic signal, German commanders drew the conclusion that the radar stations were far more resilient than they'd believed. The open steel lattice towers had survived the bombs, that much was clear from reconnaissance photographs, and now, apparently, even the destruction of the station's buildings and equipment wasn't enough to silence it for more than a few hours. The Germans had no way of knowing that the signals they were detecting came from a completely different station, that Ventnor was actually a smoking ruin with desperate crews trying to rebuild it from spare parts and improvised equipment, that mobile radar units were being rushed to temporary positions to fill the gap. On August 15th, 3 days after the attacks, Hermann Goering held a conference with his commanders to review the progress of the air offensive against Britain. The discussion turned to the radar stations, and Goering made a statement that would prove to be one of the most consequential decisions of the Battle of Britain. He declared that it was doubtful whether there was any point in continuing attacks on radar sites, in view of the fact that not one of those attacked so far had been put out of action. This assessment, based on the false signal intelligence showing Ventnor still operating, led to a strategic decision that the radar towers were too difficult to destroy effectively, that the effort required to attack them was not justified by the results. The Luftwaffe would instead concentrate on destroying RAF airfields, aircraft factories, and eventually British cities, leaving the chain home network intact and operational. German intelligence had made a catastrophic error, mistaking a clever deception for invulnerability, failing to understand that sustained attacks on the radar stations, particularly during those vulnerable days when Ventnor was actually destroyed and others were damaged, might have blinded Britain's air defence system at the crucial moment when the invasion was being planned. The truth was that the radar stations were quite vulnerable to sustained attack, not to the towers themselves, which were indeed hard to destroy, but to their supporting infrastructure. The wooden huts housing the receivers and control equipment were flimsy structures that burned easily. The power supplies could be disrupted by cutting cables or destroying generators, and the telephone lines connecting the stations to the filter room could be severed by bombing the junction boxes and repeater stations. Had the Germans understood the system's architecture, had they recognised that destroying the information network was more important than toppling the towers, had they maintained pressure on the radar chain during August 1940, when Britain's fighter strength was stretched thin, they might have created the blind spots needed for successful air attacks. But Goering's decision, influenced by the Ventnor deception and a fundamental misunderstanding of what made the system valuable, meant that the attacks on radar stations essentially stopped. Over the remaining months of the Battle of Britain, some stations were hit incidentally during attacks on nearby targets, but there would be no more coordinated efforts to destroy the chain home network. The operators at Ventnor, working around the clock in shifts that sometimes lasted 18 hours, achieved what their commanders had thought impossible, restoring the station to partial operation in just 11 days. They cannibalized equipment from training facilities, improvised solutions using components never intended for the purpose, and on August 23rd, Ventnor's distinctive signal appeared on German monitoring equipment. But this time, it was real. The station was actually operating again, detecting aircraft and feeding data to the filter room. The complete restoration took longer. Permanent repairs to the transmitter facilities and receiver huts stretched into September. But the critical early warning capability was restored far sooner than anyone had expected. Throughout this period, the deception continued, multiple stations adjusting their outputs to mask any gaps or weaknesses, creating the impression of an unbroken radar fence that made German planning more difficult. and reinforced their belief that the radar stations couldn't be effectively attacked. The strategic impact of the Luftwaffe's decision to abandon radar station attacks cannot be overstated. It essentially guaranteed that the Dowding system would continue functioning throughout the Battle of Britain, that RAF Fighter Command would retain the early warning and ground control capabilities that multiplied its effectiveness, and that German bombers would never achieve the surprise necessary for devastating attacks on British airfields or cities. Throughout August and September 1940, as the battle reached its climax with massive daylight raids on London and desperate fights in the skies over southern England, the radar network continued providing the advance warning that allowed Britain's outnumbered fighters to intercept raid after raid. The Germans would comment with frustration in their after-action reports that British fighters always seemed to be waiting for them, positioned at the right altitude and location, that the element of surprise was impossible to achieve, that they were fighting against an enemy who somehow knew their every move. What they were experiencing was the practical effect of integrated radar-based air defence, a system that turned aircraft detection from an uncertain art into a precise science. The chain home network expanded throughout the war, eventually growing to over 100 stations covering all of Britain's coasts. And the technology evolved with new developments like centimetric radar, using much shorter wavelengths that could be mounted on rotating antennas for better direction finding. The cavity magnetron, invented by British scientists in 1940, produced far more powerful signals at microwave frequencies, allowing compact radar sets that could be carried by ships and aircraft, leading to systems that could detect submarines on the surface and guide night fighters to enemy bombers in complete darkness. The British shared this technology with the United States through the Tizard mission in the summer of 1940, bringing sample cavity magnetrons to America, where they were described by scientists at Bell Labs and RCA as the most valuable cargo ever brought to American shores. The Radiation Laboratory at MIT was established to develop applications for this technology, and within months, American engineers were producing radar systems that would be used on ships throughout the Pacific War and in bombers flying missions over Germany. The psychological impact on German aircrew of facing an enemy who always seemed to know they were coming was enormous. Pilots and bomber commanders writing in their diaries about the eerie feeling of British fighters appearing exactly where they were most vulnerable, of being intercepted before reaching their targets despite approaching through clouds or at altitudes where visual spotting should have been impossible. Luftwaffe intelligence officers spent months trying to understand how the British were doing it, developing theories about spy networks, about observers with binoculars stationed all along the coast, about some kind of sound detection equipment, never quite believing their own reports about the radar towers because they couldn't accept that such a primitive-looking system, using long wavelengths, could be so effective. German radar development had focused on shorter wavelengths and more sophisticated technology, producing equipment that was technically superior in some ways, but never integrated into a comprehensive air defence system the way the British had done with chain home and the Dowding system. The Germans had the pieces, but never assembled them into a functional whole, remaining focused on tactical applications rather than the strategic integration of detection, communication and command that made the British system so powerful. In the final analysis, the decision to stop attacking Britain's radar network represented a failure of German intelligence and strategic thinking that contributed significantly to the Luftwaffe's defeat in the Battle of Britain. The towers that Elizabeth Henderson and thousands of other WAF operators and RAF personnel kept operational through the summer and autumn of 1940, sending their invisible radio beams across the channel to detect approaching raiders, multiplied the effectiveness of Britain's fighter force, to the point where roughly 900 fighters could defeat a German air force more than twice their size. The Ventnor deception, that clever improvisation to make a destroyed station appear operational, influenced Hermann Goering's strategic assessment at precisely the moment when sustained attacks might have blinded Britain's air defence, leading to a decision that preserved the very system that was defeating his air force. Winston Churchill would later write that the Battle of Britain was won by the skill and courage of British fighter pilots, the famous few who flew Spitfires and Hurricanes against overwhelming odds. But he also acknowledged that radar gave Britain an extraordinary advantage, allowing those limited fighter resources to be used with maximum efficiency, ensuring that every scrambled squadron had the best possible chance of intercepting enemy formations before they reached their targets. The legacy of chain home and the Dowding system extends far beyond the Battle of Britain, establishing principles of integrated air defence that remain fundamental to military doctrine today. The integration of detection systems with command and control networks, the importance of filtering and correlating information from multiple sources to create accurate situational awareness, and the multiplication of defensive capability through early warning and coordinated response. Modern air defense systems, with their sophisticated phased array radars and computer-driven command centers, are descendants of the system that Robert Watson Watt and Hugh Dowding created in the years before World War II, refined through desperate necessity during the summer of 1940. The story of how Britain's radar network survived and functioned throughout the Battle of Britain is ultimately a story of technological innovation, strategic deception, and the failure of an enemy to recognize what they were really fighting against. Those tall steel towers rising from the British coastline, dismissed by German intelligence as too primitive to be truly effective and too resilient to be worth attacking, represented the difference between invasion and survival, between defeat and victory, between a world where Nazi Germany dominated Europe unopposed, and one where Britain stood alone but undefeated, waiting for allies and building strength for the eventual liberation of the continent.